All right, so I will start on a little presentation I made this week on deep learning and time series. All right, so we're going to talk about time series and using deep learning to address them. And we'll use two examples, COVID and hydrology. Well, let's first decide what a time series is. So maybe the most primitive or basic time series is a set of events which are labeled by certainly time and also some sort of other label which designates the type of event. If this was an earthquake, the time would be the time of the quake, and the X was the position of the earthquake. And there is a huge number of time series which are called geospatial because the X is part of the space on Earth. And we will call those geospatial time series. And often those time series, it's important to know that X is has geometrical properties like Euclidean distances, and points are near each other in space, because points, if let's say if this was not well, if earthquakes lie on faults, and faults lie on a particular part of the world, so and they're near each other. So so those are, I will use geospatial for those time series where such proximity is important. So, however, the work we'll look at today is not really it is geospatial in that it's stuff about Earth and it's labeled by positions on Earth, but they're not specially correlated by position. And the fact that when we're looking at COVID cases in Chicago and Los Angeles, we're not using the particular location in space of Chicago and Los Angeles. We're just using those as two different sampling points for COVID cases. Now, every event in a time series has some attributes. In the well, I mean, actually, polling is an example of such events. When somebody interviews somebody to find out how they view the president or who they're going to vote for, that is an event, because then it's labeled possibly by the person who responds, the polling company, and the time. If we look at earthquakes, which is in the next bullet, those have spatial geometry, and there the value of I runs over the magnitude of the earthquake and possibly the depth. The depth you could view as part of X, but typically depth is not viewed as the spatial position. The X is, in most geospatial time series, X is the 2D space on Earth. An important type of event is what I'm generating now. I'm generating events where the characteristic of my events are audio signals. And every now and then I issue a new audio signal into the world. Here the location X is labeled by me, the person, or maybe it's labeled by your Alexa speaker, and I is whatever you use to get the tokens which you use to represent the speech. or however they're processed by Fourier transforms and things. So actually, speech is possibly the most important time series, in that it's where most of the work from industry has gone into speech processing. So now we have these events, and we want that there are approaches to time series where you look at events. However, there's also a very common approach, which is to take these events which are scattered around in space and time and consolidate them into bins of space and time. You say, here is what happens in this region of space, here is what happens in this bin and time. And often, like in the case of COVID, the binning is typically daily, or you also could be weekly. In the case of earthquakes, you can even do it annually, but also probably earthquakes have quite a lot of fine time structure, and even daily is pretty coarse. If you look at how data is reported, COVID data is collected as events, but is reported as daily. The USGS earthquake data, the Geological Survey earthquake data, is collected as events, and you have to bin it by hand. And so from now on, we're going to look at these, what you call classic time series, where everything has been binned in space or time, space and time. Here's a topical example of a daily time series for COVID from the Worldometer record, one of the many sources of COVID data. And at the top, you have the daily signal for infections, and here you have fatalities. And I put these snapshots at the bottom while I was writing the talk. And you can see, actually, these things that are reported daily are really events. Like at 2:30, they got 68,500 US cases. At 6 o'clock, 138,800. And at the end of the day, which for them is around 9:30, it's 161,000 events. Actually, I think this is possibly one of the largest recorded days in the US. So this is an example where it is binned at the source. I don't believe you can get from Worldometer the data, the daily data, but you can't get the event data. And it's not so obvious whether the event data is meaningful, because the events here are just people reporting, and when they decide to report during the day is pretty unclear and not terribly fundamental. All right, time series. Well, here's actually an example of the work I was doing with Gregor, showing actual spatial data. So here we have New York and Chicago, Cook County and New York City. These are actually some time ago. This is data till the middle of the summer, and it has the number of cases per day and the and the number of what is this? This is fatalities and this is cases. Yes, the scale is very different. Cases are 4,000, fatalities are 400. And you can see the data is actually pretty different between Chicago and New York City. You also see obvious fluctuations here. This is typical of observational data. It's sort of slightly dirty. Anyway, we're interested in understanding sets of such data, where in this case they're labeled, these are, although it's New York City, it's really whatever county New York City lives in. I think it's presumably New York. And Cook County. The data tends to be collected by counties. And we have whatever it is, 314 counties across the US we looked at data for. All right, so I've already said the first 2 points. Things either they can be naturally binned or not naturally binned, then you have to bin it yourself. Another word for time series, which is relevant, is sequences, because a time series is a sequence. You have something that happens on day 1, day 2, day 3. That is a sequence. And the word sequence is actually what is more often used in the natural language processing field, because when you look at text in a book, that is a sequence of written words, or if you listen to somebody speaking, that's a sequence of spoken words. And the study of sequences, time series, or which is as sequences, has 2 important things you try to do. One is so-called sequence to sequence. That is typically what you want to do with natural language processing. The input sequence is the audio signals from me speaking. The output sequence is mapping that into words in a text file. Or another obvious example in this same field is taking text in one language and converting it to text to another language. So that's what's called sequence to sequence mapping. And that should be distinguished from forecasting, which you could call sequence to future. When I type my Gmail, Google likes to predict sometimes what I should finish the sentence with. It often tries to autocomplete my sentences. So that is sequence to future. It's taking the input sequence I type in and is using a deep learning network to predict the future. And when we're doing in the field of earthquakes are almost all forecasting, because the thing you desperately want to know is, will there be a large earthquake in this region in the near future? So sequence to sequence is important and sequence to future is important, but they actually mathematically have the same basis because both start with sequences or time series. And if we go to environmental science, I could take the daily rainfall and temperature and do 1 or 2 things. I can predict the future rainfall and temperature, or other type of environmental properties, or I could actually predict what's happening now, namely maybe how fast the plants are growing, the crops are growing, so I can make agricultural forecasts. Another example we'll come to is Newton's laws. Newton's laws give time series. The equation mass times acceleration equals force is an equation which allows you to predict the future position of particles. There is some sort of other related data. I even gave an example of that, which is electron, which I didn't really give. Sorry, I didn't give an example of that yet. It's election polling. I'm too busy remembering what I've been doing over the last couple of weeks. So election polling is sort of a time series in that you get new polls every day, and you're desperately trying to do a forecast. And they didn't actually do so well this year. And as far as I know, they do not use sophisticated time series methods in election polling. Maybe they should. Maybe they should. All right, so now let's come and have a little discussion of predicting the future. And it's quite useful to look at how the future is predicted in physics. So we use something like Newton's law or Schrodinger's equation or Dirac's equation or what have you, Navier-Stokes equation. We use some physics-based equations which allow you to take the position/velocities of particles at one time and predict the next time. So here is a very simple example in these bullets here. We have the formula for the acceleration. As we assume we know the force, then we discretize the velocity to show that to predict the velocity from the acceleration and the position from the velocity. And the force could either be constant, like if it was gravity, or if I was doing molecular dynamics, the force would strongly depend on the positions of the particles. And but it would be known. And so the feature of this formula, Newton's law, is sort of interesting. It says we have an operator. We can think of these three equations, an operator allowing us to take data, initial data, say t of 0 and 1, and predicting the future. And that operator, however, is sort of a universal form, but it has data in it which depends on what we're trying to predict. In the case of particles, it would be the nature of the force, which could actually be could have a lot of particle dependence because chemical forces are very position dependent and type dependent. And of course, the mass is certainly particle dependent. So I would say the goal of deep learning, you could argue, is to derive the equations, the operators analogous to Newton's laws for general time series. And when we think how to do that, we should notice that this analogy tells us that we would expect we're going to try to derive an operator for New York City and an operator for Bloomington. We want those to have some universal form, but differ in two ways. They'll have different initial conditions and different parameters. In the case of New York City, there will have to be some parameter reflecting the number of people. It could just be the initial conditions. And but that parameter would put in social distancing and things like that for COVID. So here's some work I did with earlier this year, well, the beginning of the calendar year, with a graduate student, JCS, and Vikram Jadea, who's a nanoengineering faculty member. And we basically taught a deep learning network, which I will explain in a little more detail, how to replace Newton's laws. And if you look at these things that are wobbling around at the edge here, these four here are four views of the actual Newton's laws calculation of these 16 particles. These are effectively chemicals interacting with the Lennard-Jones potential. And here is the result from the neural net. And it's not so important for this particular study, but this neural net has sort of different properties from Newton's laws in that it actually manages to learn how to predict a long time into the future. It goes 4,000 times further into the future than the discretized equations of Newton. However, it has one feature, namely it has 65,000 parameters in this recurrent neural net, which we will discuss. And to find this deep learning network, you have to first calculate a sample of these. You calculate a set of time series where you know the answers, and then you train the network to reproduce those time series. In this case here, we had around 5,000 training time series in the training set. So if you look at actually deep learning, it's worth noticing it does look like an operator. Namely, if you take inference, you take some values, you apply the deep learning network to it, and then you get an answer. So think of a simple, fully connected network. You put in the input, and out pops the output. So that's an operator. So we can think of deep learning as providing us operators, and our goal here is to try to find, when we have one example of an operator for time series, Newton's law, and we're now going to see if we can't do time series operators for other fields. In fact, I don't know why you couldn't do all fields. You could just study all fields in this way. All fields which give time series, which are a huge number. Here is more results from that work with Vikram and JCS, and this just takes three different potentials here: simple harmonic oscillator, double well. Here's the Leonard-Jones. This is just one particle, and these numbers here are the errors, which are a small and effectively flat in time. And if I did molecular dynamics, the errors would explode in time. And these time intervals are very small. This is the molecular dynamics has already gone wrong at a time step of 0.01. And these things here, this biggest time step is 4, which is 400 times bigger than when the classic molecular dynamics got the wrong answer. All right, so it just says that deep learning is quite subtle and can do some interesting things. So here's the work I did with Gregor, who's also on the call. And this is just an introduction to this set, which basically says everything I've said already. Well, it summarizes what I've said already. And it points out a few other examples where we'll mention this at the end if we have time. Some of the best work on time series has been done in studying traffic, because traffic is an obvious time series. If you look at, if you take the roads, you can calculate the number of cars passing you at a particular time and just plot that as a function of time. That is a time series. And so you can use these time series to predict the time it takes for to travel a particular route, and even by comparing the time series of traffic patterns, you can predict the right route to take. And this time series study of traffic has been extensively pursued by Uber and Didi, and presumably also Lyft and the other companies, to optimize the routing of their cars. Okay. So here is a picture of the problem we're looking at in a somewhat abstract fashion. So this is these things here. We have time running up this way and space running this way. So in the case of COVID, each of these columns is a county. Each of these dots vertically is a day. And we have over 300 counties and over 200 days. And then if I was doing, say, natural language processing, each of these points here will be a sentence, and these will be the tokens which make up the words, which then make up the sentence. So this will be the sentence broken up into the fundamental audio components. And but the picture's still the same. We have a set of we have a collection. I call it the bag, because this is what's often used in this computer science areas to denote collections which don't have obvious structure. And so that's what's true here. There is some structure, because in a book, sentences near each other are likely to have some context in common. And in the case of COVID, there is actually connection, we know, between the different counties, because one of the main reasons COVID spreads is due to travel, and people bring it with them as they travel. Anyway, these two red bars tell you the two things you do with this spatial bag. So we have the spatial bag, which is the data. Then we either forecast the future, like the number of fatalities in the next month, or we forecast the present, such as if this was English, this could be Turkish or something. But I also pointed out that in the case of Newton's law, each of these columns is defined by parameters. Those parameters are twofold. There are the initial values of the columns. That primes the pump. When you solve time-dependent differential equations, you need to have initial values, and that's the values on these first few time values. The same is true in deep learning. You need to prime the pump. In fact, you need a bigger priming for deep learning than you do for Newton's laws. And then the other thing we have associated with each of these columns are the equivalent of the mass and the force, which in the case of COVID is some static parameters telling you, or possibly dynamic, telling you what's going on at that space point. They could be a dynamic parameter measuring social distancing, or an effectively static parameter measuring the fraction of senior citizens in the county, or the fraction of people with asthma or kidney disease and so on. So because it is meant to be that COVID is impacts different people of different age and different medical conditions differently. So this operator will depend on these input properties. So we have input properties, which are going to tell us the operator. We're either going to predict to the side, that sequence to sequence, or we're going to forecast the future. And the future can predict many different things, and it can also predict quite a way into the future. All right, that's the problem. And at least I know of two pretty different methods. Both methods were originally developed for natural language processing. One is recurrent neural nets. I already pointed out that's what we use for solving Newton's laws problem with JCS and Vikram. And they feed us, they take sequences or windows of time values and pass them through a common neural net, which extracts information, including a tag for the future representing the essential features of the initial data. They're actually pretty difficult, in my opinion, to really understand. These are actually quite old. They were invented at the beginning of deep learning, I think well over 20 years ago. And they're not so easy, I think, not so intuitive. In detail, then qualitatively, they're intuitive. The newer methods are actually easier, in my opinion, to understand. They're called attention-based methods. And there are some papers saying that attention is replacing recurrent neural nets. I don't actually think that's true. I think both are quite interesting. And the reason why we'll see what an attention-based method is, but it's not certain. If you look at the world, there are at least sort of two types. There are many types of problems. If you look at natural language processing, it is sort of a classification problem. You have a dictionary. I don't know, maybe Grammarly tells me I have a big vocabulary, and I only use 6,000 words a week, different words each week. And I'm sure that the modern NLP systems have 50,000 different words in them. And NLP is classifying, it's trying to take the input and classify the tokens and collection of tokens into words in a dictionary. When I'm doing COVID or earthquakes, I'm feeding in numbers, which are the magnitude of the earthquake or the number of COVID infections and fatalities, and I want to get other numbers out. So it's actually doing arithmetic. And so they're pretty different. Classification, I mean, you can say arithmetic is classification, namely, you're trying to say, well, we're looking for the number of COVID infections, we want to see if we want to classify tomorrow's infection as 150,000 or 150,023. So choosing a different number is sort of a classification, but I think it's clearly a different type of classification from the one used in text, because text has a set of discrete items called dictionary entries, which are pretty different, and you're trying to choose between them. In the case of numbers, you're trying to calculate numbers, and the numbers are smoothly varying. So it is not so obvious that NLP and science and what I call them technical time series, that means they have numbers in them, are the same. I notice if you read the literature, if you go online to medium.com or inside towards data science, whatever those blog systems are, you'll find lots of articles about BERT. And BERT was a famous natural language processing system called the bidirectional encoder representation. And it comes from Google and was a step above previous such systems. And it uses attention. It uses transformers, in fact. It wasn't the original transformer paper, but BERT was the most famous implementation of transformers. Here are just a few slides, which some of you may know well already. Namely, here is a recurrent neural net, and they have weights. These weights are matrices and biases, and you feed in the x sub t is the value of the time series at time t, and it actually could be a vector because you can have lots and lots of inputs at time t, and that's fed through a network where it actually gets a input, the history from the previous time, does an operation, and then passes off the next history, which goes to the next time. And these W and U's are universal, namely all times have the same W and U's. In fact, if you do a spatial bag, every member of the bag has the same W and the same U. The different bag members are actually only distinguished by the X's, because the X's will have these parameters like percentage of senior citizens in them. And here is a picture I grabbed off this web post on recurrent neural nets, and it's so-called, it unrolls that to actually say in a little more detail what happens. You feed in the X's, and you have the same weights in every one of these green boxes, but because these are feeding in different X's and also getting different histories, these H's are repeated here. They are actually simultaneously analyzing all of the X's to get the answer. And actually, these things can either, if they're used for sequence to sequence, then you take these H's and you get those answers. You feed out things from each member of the recurrent network. In the forecast mode, you just take the output of the last time value. And actually, that's what I typically, for the work we present today, we're doing sequence to future, not sequence to sequence. But the same network will do either. And there's also same is true of transformers. They can do sequence to sequence or sequence to future. Now, recurrent neural nets were a brilliant idea, but didn't actually work very well. And they couldn't, they were bad at calculating derivatives for the back propagation, and they could not easily forget things. And so the actual network, there are two things called a GRU, which is pretty similar to an LSTM, and they have a choice of, they have a little more complex here. You have 4 equations here, But they're still sort of similar in their collection of matrices W and U. The U's multiply the H's, the history, the W's multiply the inputs. So they're actually different sizes because W has one part of the W, the second dimension of the W is this number of independent nodes in the neural nodes in this green thing, and but the input number for W is the number of input parameters. U's are square matrices, number of neurons times number of neurons, because the H's, they have input which is an internal input called H. That's what it tries to say here. H is the number of neurons in each layer in each cell here, and W is the H times the dimension of the system, the input feature size. And this multiplies by X, which has dimension D. And here's LSTM, which is like GRUs, which are more complex. My intuition is that vanilla neural nets don't work. GRUs and LSTMs do work. We always use LSTMs because it's not worth the bother, because they work nicely and it's not so obvious that we need to change them. They are very similar to GRUs, slightly more complicated. Here is an example of this thing I already showed you with JCS and Vikram, which shows that we input at the bottom here, we input the time sequence, which is the sequence is actually pretty short. It's of length 5. I should also point out the length of the sequence varies quite a lot from application. For that work with JCS, he used a time series sequence length of 5. If you're doing BERT, it will be significantly longer because it will be the sequence length to capture a sentence or two in terms of tokens, and those tokens are subparts of words. So anyway, you have a number of sequences. In the case of this hydrology we're going to look at, some of the work in that thing has used a length of 270. So we have here a sequence length, which can run from probably 5 is about the smallest you could take, 5 to 270, we could say, although 270 I think is quite large, and we don't get good answers when we run with 270. We prefer smaller numbers like 20 or 30. That runs through 2 layers of these LSTMs. Here's the first layer of the LSTM. And there's the second layer. So each of these layers can be unrolled to get a set of cells of length equal to the sequence length. And then out pops the results, and then they pass through so-called feed-forward networks to get the output. And here's the output, future predictions. As I said, we could get answers from the side, but as we're not doing sequence to sequence, but sequence to future, we ignore the answer from the side. And if you go to like TensorFlow or PyTorch, there's an option as to whether you want to keep the answers from the side, the sequence answers, or just look at the future answers. So here's just an example of explicitly unrolling the LSTM. We have here just 3 of the X values, and here we filled in the details for one of these, and here we have the H's coming along here. They're going off to the side, which we typically ignore. Here is the preserved content, and those 2 are fed forward, and they go right the way through the system. And the system then calculates this full sequence at a time. And well, here's just an example of what actually, to show this stuff works. This is actually the total data summed up. This has 314 cities, so you can't really look at 314 pictures. I showed you actually 2 results from this analysis, for Chicago and New York City, but we don't really want to look at the other 312. So normally we just look at the sum of all the cases and the sum of all the fatalities. The fit is done to individual cities. No, well, I should say it's done over the sum. The loss function is the sum over cities of the predicted values, which for this problem, the predicted values are the infections and the fatalities. But it actually doesn't just predict it for the next day at the end of the time sequence. It predicts 2 weeks in advance. And that's shown by these blue curves here, which are the predictions. Those predictions go to the future. And it's sort of one interesting feature here is it learns the weekly structure of this data quite reasonably. This data is full of errors, I'm sure, because people misreport and forget and late report, and so the data is not that precise. But it's clear the basic structure of this data is reproduced. There are some anomalies, like here. We have a pretty serious miss here where the data is much smaller than we predicted this is a weekend. These dips are typically Sunday and Monday. I don't quite know why people don't report on Monday, but they don't report on Sunday or Monday. Nearly as many. They're not nearly as many, especially for fatalities. The dips, the fluctuations in fatalities is much larger than the fluctuations in cases. The same is true today. If you just look at those results I showed at the beginning, those daily fatalities are fluctuating much more than the daily infections. All right, now we come to this attention-based system, which is actually, in my opinion, simpler. It's pretty hard. It's harder probably to use because there's not so much experience with using it, but it's simpler. It does not run through things as a sequence. It actually presents the data as a set of time series. You hand the transformer. Well, in the case of COVID, you might hand the transformer 314 time series, which were the time series which start at a particular time over all the cities in your study. Or you could just do a smaller number of cities. It's really up to you. And the key for transformer, but in the transformer, whereas in the LSTM, those are just done sequentially, one after another. In the transformer, they're done simultaneously. They're not done in sequence. And the critical thing is these things called Q, K, and V. And the transformer is sort of interesting. That it's clearly looking for patterns, and we'll see. There's lots of interesting comments here, but let me just go and look at the patterns first. Yeah, let's just vectors Q, K, and V. All right. So you form, when you take any one sequence, you have a sequence that's specified by an initial time value and a spatial point, you're going to form a vector. You're going to form a Q, K, and V for that. And Q, K, and V, which are shown over here, the Q is the query, K is the key, and V is the value. So what happens? Along comes one time series with its Q. It matches that Q to the K, and if there is a match, namely the Q and K have a lot of overlap, it identifies that we should look at this V here, which is the value or vector for the city which had key K. So it has Q. We have I running over space points, K running over J running over space points. So we take Q of I, the query, the key from J, the value from J, and then we add this result here, which is sort of a matrix multiplication. We add it to the ith, the attention for the ith spatial point. And now we can come back to what it says here. So it uses a softmax, which is a way of actually accentuating differences in sizes, and it uses a softmax to identify which to rank the matches between Q and K and choose the largest matches. Now it says multi-head. Well, that just means you have lots of QKVs. You have maybe 8 different QKVs. The Q and the K and the V are just learned. They're gotten by taking the input for that time series and feeding it in to a dense matrix, a dense network, and looking at the answer. That's sort of what is called embedding. Embedding corresponds to taking the input and feeding it through a network to get an answer. That's called embedding. And you actually always start these problems off by doing an embedding. You take whatever this input is, which is a mixture of static spatial values and dynamic spatial values, and you feed those inputs through this neural net to get you an embedded output, and that output is the one the neural net deals with. Another interesting thing these things have is positional encoding. You do a positional encoding by actually adding a new property for every time series, which is its time value. So in the case of one reason I got such a good representation of that weekly time sequences, I added in a weekly positional encoding, which you do by actually taking cos theta, sine theta, and adding those as two new properties where theta runs from 0 to well, I don't know, 0 to 2 pi over the week. And I either do that for weekly or annual. All right. Now, what this says here, the original attention is this architecture here. We're full of these attentions and multi-headed. This is called the what is this? This is the encoder and this is the decoder. Now, in the case of the scientific time series, because we're not doing classification, it's not so clear to me whether this works. So I changed it to do an encoder, which is the multi-headed attention. And what that does is it goes in, applies these QKVs, and it identifies magic patterns that it's found by comparing the time series. Then those magic patterns are merged with the actual input value, and they're fed through a classic LSTM, because LSTMs are very good at doing number crunching. So that's how, and so this is one way of doing it, a pure LSTM. Or the other way of doing it is to do an initial identification of attention, which, if you like, is the patterns. The famous example of patterns is what is it? I think there's a singer called Taylor Swift. Now that says, if you see the word Swift in certain types of sentences, you should look for the word Taylor, and because there's a magic connection, which would not normally be true. Normally tailors would mend clothes, and Swifts would be birds or something. But Taylor Swift is a correlation, so that's a pattern. George Harrison or Donald Trump are patterns which are correspond to connecting two words together. And those patterns are learned by this attention mechanism. All right, so that's that. So that's what I said here. So I think an interesting feature of attention, it really focuses on patterns. And it's not quite certain how you're meant to do patterns for big problems. In the case of natural language processing, I gather they just look at patterns around local sentences. In the case of COVID, we have 314 counties and 200 days. For the hydrology data, will show I have 671 locations and 7,000 days. And quite how you do the patterns is not obvious. I use a random sampling to look for patterns. And you can look for patterns in all sorts of different places. You look at it in time, in space, or all over the place, space and time. As far as I know, it's a research issue, which is the right one to do. And this also could be different in different problems. And initial results, COVID does better when I do a random search over the entire space. In hydrology, I do better when I look in time for the sequence, matching sequences in time, patterns in time. So here is transformer results for because the transformer has to look at this matching. You actually get an error. You can get different answers to the transformer depending on how you do that matching. And so that's used to get an error estimate here for the predictions. One of these is the real values. You can hardly see it. It's buried inside the prediction. And here is the error, which is this is smaller than for the LSTM. This error. This is probably our best fit to the COVID data. So this is the original sample you had, which is fewer cities and fewer days, which also is quite a good fit. Here is the transformer applied to this COVID data and here you can see some of this data is pretty messy. I showed you New York City, which was big peak at the beginning and not so much thereafter. Here is King County, I think that's Seattle in Washington, and you have a more double peak, but there's huge fluctuations. That's because, especially at the beginning, they really reported in a funny fashion. I should also, while I'm here, point out there's what else you have to do. When you prepare the data to feed into these neural nets, you have to make certain the data is normalized properly, because 1 is a magic number for a neural net, because these things have these activation functions have 1 as a special number. And so you better make certain that you don't make your numbers so way off in magnitude that they always get killed by these activation functions. So although they're plotted as cases, they're not processed as cases. They're processed as actually the square root of the case is first taken, and then the square root of the cases is normalized to lie between 0 and 1. All right. So here, this is Los Angeles, which is very different. Which is an example of one of the places where the COVID came later, and Los Angeles and Seattle. This is just a different fit with more, somewhat larger error. When you have less data, you get larger fluctuations from the hybrid transformer. It's again a pretty reasonable fit. Again, that's the same, similar data to before. Oh no, I went backwards. Okay, all right. All right, so now we come to the hydrology data, which was with Niranda Perrara, who prepared the data for me. So this data comes from the USGS, and it has 671 locations in the US. They're each patches of land around 300 square kilometers in size each, and they're called small or medium size. And they have some dynamic data, which is the daily rainfall, the precipitation. Short wave is called visible light, or visible light is called short wave as opposed to long wave. And this is just the amount of energy being deposited in that region by the sun. Here we have the daily temperature, maximum temperature, minimum temperature. Notice, of course, that does vary as a function of time in a continuous fashion, but there is a daily maximum and a daily minimum. We have the vapor pressure and the average vapor pressure for that day. And here we have what they're really most interested typically in predicting, the so-called discharge. How much water is released by this basin? And then we have all sorts of catchment. These are called catchments, water catchments. These are static properties, including some which are related to the dynamic, like mean precipitation. There's aridity, area, elevation, and so on. Fraction of snow, mean slope, amount of rock types and clay and stuff like that. And some of these I forget what PET means now. I did look these up once. All right, so we have around, I think 27 static variables, which is actually pretty similar to what we had in some of the COVID analysis. The COVID analysis had between, the final analysis only had, I think, 12 static variables because they'd consolidated a lot of the variables into some composite variables. Originally, we started off with over 30 static variables, which were rather fine-grained. I should say neural nets are very tolerant of the number of variables you use. You can do giant numbers of variables, and I don't think that affects its convergence. All right, so here we have, this is hydrology data, and this is the rainfall here. So I'm just trying to reproduce the whole data. The one that's reproduced worst is the rainfall. That's because it fluctuates a lot. And in fact, when the professionals tackle this problem, they do not try to predict the rainfall. They input the rainfall and predict the runoff. And as we'll see, the runoff is predicted much better than the rainfall. Notice the rainfall is input. So it says there's so much fluctuations in rainfall, which we know there is. Rainfall is pretty random. And here we have the solar radiation. We're feeding in this data and then predicting the future for this data. Here we have the minimum and maximum temperature. I notice each of these things here is a year. This is 20 years worth of data. And I did annual time encoding. So it's fed in cos theta, sine theta, where theta goes from 0 to 2 pi over a year. And that gives it a little sequence it can use to match to these this annual dependence in this data. Here we have the vapor pressure on the left, and we have really what we want to predict, which is the runoff on the right. I should say there's a slight subtlety in this plot, and that sometimes there is no real value, and there is effectively a real value, but it can't be plotted in the sum, because this approach allows you to have missing data, and sometimes they do not have the runoff for a particular location. If you sum over 671 locations and you have 2 missing data, well, we actually put 669 points into the fit and calculate the loss for them, but we can't plot the total because we're missing 2 values. And so that's why this thing is shown, there's no prediction here. But I'm sure the prediction will be good if we do, because there are not very many missing values. There are 2,000 missing points over the entire data sample, which, as you see, is quite big. Here is just coming back to the initial plot, the rainfall plot, to explain why it looks so ratty. This we plot on a finer time scale, so you show this is 1,200 days, not 7,000 days. There's six plots to represent one, and you can actually see better that it's just due to occasionally having rapid fluctuations, day-to-day fluctuations. There's that rainfall data. So here is some comments on this. So this was all run on Google Colab Pro, which I recommended to you. For COVID, it's 5 to 10 seconds. For hydrology, the one I'm running now, which has sequence length of 120, and all those space-time points, it takes 1 hour per epoch. And so in fact, it crashed overnight because Windows rebooted itself. So I've told you we use positional encoding for COVID weekly, for hydrology annually. And I've told you this is quite clever in my opinion, this weekly encoding. I also add to this not just the weekly one, but the linear one. This is a number that goes from 0 to 1 as you go from the first space point to the last space point, and you have another number going from 0 to 1 as you go from the first time to the last time. And notice all these so-called these positional, either in time and space encoding, they're just added as properties of each time series. So you add, in this case here, we've added 4 properties: a cos theta, sine theta, oscillatory property, and a linear property in space and time, total of 4. The cos theta, sine theta being in time. And I believe that encoding significantly improves the fits. These, as I said, are the input data. We input these 4 encodings. Towards the end, they added social distancing, which was time dependent, to the county data set. And we have actually 34 predictions. We have the next day and then further 14 days, so that's 15 days times 2 for the COVID, which is 30. And we also predict the 4 encodings. So you predict 34 numbers at the end of each time series. And you can only predict the future if the time sequence ends. If the time sequence ends less than 14 days, more than 14 days from the end. So you only get the future as a prediction for, which is most of the time series, those which don't come up right to the final time value, because then you do not know the future time value. But it's okay as far as I know. You just ignore it in the loss function. This is a convenient, the loss is a sum over predictions. Use mean square loss, and that's the sum over predictions. You can just have some things not predicted. It's really not a problem. I've already showed you that we pointed out that we have we summed over cities. I took the square root. Actually, on the hydrology data, I took the cube root of some of the data to try to. I mean, I looked at the data and tried to choose the right processing function. Actually, for the earthquakes, you take the log, because the magnitude is the log of the energy, and energy is actually what's is the real physical quantity. So you can take log, fourth root, third root, square root, and these are good ways of squashing data, so that you, because you really want to not only have data that lies between 0 and 1, you want it to have a decent standard deviation. You don't want it all. If you have these data sets which have a lot of extreme values, if you just scale it between 0 and 1, all the points will be small. Nearly all the points will be small, and there'll be a few large values. If you take the third root or the fourth root or the log, you will get a much better standard deviation and a broader range of input values. I pointed out this problem here with that there's just a lot of things you can calculate attention to. And in the case of COVID, I took 314 by 9, time sequence of 9. Hydrology has been a little more, even more wider range. And you say, I just do a Monte Carlo sampling of this giant space. I use 4 heads for COVID and 8 heads, 4 or 8 heads for hydrology. The last slides tell you what's in the notebook. And if you look at what you have to do this, there are 3 types of processing. There is the processing which is entirely dependent on the problem. So you try to do that on in a separate world. Like in the case of earthquakes, we bin all the earthquake events in a separate program before we feed it into this time series processing. Then we have some generic processing, which isn't actually doing deep learning, but is reading in the data, normalizing the data between 0 and 1 and taking bars, generating sequences. I should say that originally we generated the sequences right at the beginning, but that doesn't work for hydrology because we have 7,000 days, 617 space points. If I multiply that data set by 270 by generating a sequence of 270 for every time value, you will have zero memory left you will just crash. So the hydrology just generates the sequences at the very moment they're needed, which is when they're fed into the for each batch. It generates the sequences for each batch. We have to generate the predictions, which including those futures. We have to do this encoding. We use so-called dynamic training in TensorFlow. That's sort of non-trivial. I personally, this is not required, but I personally always, I monitor the training, and if the training has a very extreme upward fluctuation, I just ignore that. Well, I don't ignore it. I test for the sequence, the behavior of the loss with epoch, and if the loss goes up too much, I just go back to the previous loss value, and as you have random numbers and everything, it will typically converges the next time around. And of course, I told you, if you take an hour per epoch and you kind of run 40 epochs, that's not terribly safe to do that without backing everything up. So it backs all the fits up. And we have to, of course, fiddle around with the definition of the fit. And then we have, of course, design a network from lots of class instances, which you can look up in Keras or things. We have to set the value of the hyperparameters, the number of heads, the dropout. We set up a restart if necessary. We have to have a custom loss function due to the fact that they're missing variables, so you need to test for missing values and not calculate the loss. You have to do validation and batching. I pointed out you generate, actually this is what you do while the fit is running. And then of course, most of the code is actually visualization, and I showed you some of that. All right, so that's, I think is, well, we can stop there. Why don't we stop there? Well, no, I might as well finish in 2 minutes. I'll just go through this. So here, this slide here has a lot of other time series data sets, which were collected by the MLPerf organization I work with. From a fellow from Cisco who led that effort. And then I pointed out in hydrology, there are actually 129 papers on deep learning on hydrology, and they're using a giant variety of different approaches, and I'm pretty certain that they're often not using the optimal approach. And the final slide I have is they were also working on earthquakes. I don't have any real results to present on earthquakes. They're actually a little harder because earthquakes are very random. Things like COVID and runoff have some systematics to them, which come from because they're like the case of COVID. It depends on how well you're doing social distancing and things, and that makes it a certain determinist. It produces variations, but they're smooth variations, whereas earthquakes are extremely unsmooth. But still, we're trying to see how far we can go with earthquakes. So I've tried to point out how this is a pretty interesting area. Deep learning provides a very robust and interesting approach, and I try to give you an idea of what you had to do this. And the code is available if anybody wants to use it. Thank you. Questions? So if there are no questions, we'll just call it, we'll finish the session and get going on your project. Thank you.